This is called branch of index or power index, whatever you want to call it. See, he is by profession a lawyer. No, this has actually happened in New York. See, in New York, there are several divisions, I mean, something like districts. Apparently, one district enjoyed more power. He went to the court and then he argued that this particular district is enjoying more power, which he should not. What he did is he collected some data and he formulated, I mean, to put it in a nutshell, he formulated that as a simple game, proper simple game. And then he introduced power of each district, because each district is a player there. And then he showed the power which they are enjoying actually is more than what it deserves. No, that's okay, that's fine.
Quantitative measures.
That's right. Yes, it's a very simple thing. I'll tell you what the index is. In fact, that is also used for evaluating the relative importance of components in a system. That was done by people working in the reliability theory. Okay, so these two, actually this, see, let me recall the definition of a simple game, proper simple game. You have a player set, n is equal to 1 to n. This is a player set, and S is a coalition, which is a proper is a subset of n. N is called the grand coalition, and there is a function v which associates either 0 or 1, 0 or 1. If it is 1, that coalition is winning, something like a voting game. If the majority of people support the thing, then it passes. Otherwise, it fails. So something like that. So this is the game. Now, he wants to evaluate the power of each individual in a given game. This can also be looked at as a problem in a system where there are many components. If certain number of components works, then the system works. What is the relative importance of each component? So you can regard that like this. For example, let me give you a very simple example. See here, this is the hi-fi system, music system. Here you have a turntable. Or if you want, you can ask something else. Here is this tape deck. Here there is an important component without which and here speaker 1 and there it is 2. Speaker 1, speaker 2. SP1, SP2. So here the system works provided if you operate the tape deck, this functions, either you use speaker 1 or 2 or both, then the system works. Now I want to calculate, this can be treated as a simple game with 5 players. N is equal to 1 to 5. 3, 4, 5. What is the winning coalition? Let me give some number. 1, 2, 3, 4, 5. These are the 5 players. See, suppose I pick S is equal to say 1, 2, not 2. Then the music will be jarring if I operate both simultaneously. 1, 3, 4. This is a winning coalition. V of this is 1. That is, the system works because you can listen to the music. This is a very important, this is a name. What is that name? without which you can't listen in a hi-fi system. Huh? Amplifier, that's right. That's the name. Yes. 3 is amplifier. This is amplifier. So this is like that you can write out the winning correlation. That is where you can listen to the music. Okay. You can, for such a system, I want to compute the power of each component. Here there are 5 like that. So here I will do it in general, but you can keep this in your mind. Okay. So I have a simple game where V of S is either 0 or 1. And now in order to define the notion of this index, I have to introduce one small definition. Call I in N. I is one player, ith player, a pivot for a coalition, yes, if 2 things happen. One, Vi is a member of S, and 2, V of S is 1, that is, this is a winning coalition, but V of S removing the player I is losing. That is, if he is in the coalition, then he wins. If he comes out, the coalition loses. Okay, for example, in the if I remove the amplifier, it's losing. Okay, that's what it is. So this is what I mean by pivot. Call I a pivot for the coalition, yes. First of all, it should be a member of, it should belong to S. 2, it is a winning coalition, but no proper subset is winning. Okay, so then I call it a pivot. Okay, now I am going to introduce the following. Define theta I to be the number of pivots, number of coalitions in which I is a pivot, player I is a pivot. Okay. The index which he used is a very simple index, beta. I'm going to write it as an n vector. For player 1, it is theta 1 divided by summation theta I. I is equal probability vector, he makes it. Theta 2 by summation theta I, etc. Theta n by summation theta I. This is a very simple index he uses, nothing very great about it. That is, you compute the number of coalitions in which player I is a pivot. That I denote by theta I. The power of the player I is simply theta I by, I am normalizing it, nothing else. And it is very reasonable. Because if somebody is a pivot to more, then he enjoys more power. That is reasonable to expect.
So here, suppose S1 is a subset of S2. What about V of S1? How does it come? If suppose S1 is a subset of S2, we should satisfy V of S1 less than or equal to V of S2.
Yes, yes, monotonic. I assume that. Yes, I assume that. That is true, because in simple game, if S is winning, any superset is also winning. Like that, all those conditions are. Yeah, whatever reasonable condition you can impose. Okay. No, in every simple game, the player, if he is not a pivot for any one of them, he is a dummy. He is useless. You can throw him out. Okay. Each player will be a pivot for something. Otherwise, he is a dummy. Okay. Because he is not contributing anything for any coalition. Okay. So let me give you an example of a. See, the one thing is he wrote a very long article about this, which appeared in the legal journal, something like 60 pages. You can see. You go to, I mean, I don't know whether the library of ours has it, but I have that paper with me. Very long article. He's as I told you, he's a lawyer by profession. And he uses this and he convinced, the judge was convinced, and then yes, that county is enjoying more power. They did whatever to rectify it. So that's all. So it's a very simple index. Nothing, complicated. Let us, let me give you an example. I would suggest you to work it out yourself. Exercise, I'll say. See, there are 4 directors. I'll say player 1, 2, 3, 4. All are directors. Okay. And the first director has 10 shares in that company. The second one, 20. I'm writing some arbitrary thing. Okay. So there are 4 directors. Ith director has, suppose I is 3, he has 30, like that. If you have to pass any law for the particular organization, the players should join in such a way such that the sum of the shares must be at least 50. 50. At least 50. Okay. But this game is not proper, but still that index you can define. This is not a, because for example, 1 and 4 is winning, 2 and 3 is also winning. So it's not, so it is, this index you can apply even for improper simple game. There's nothing that says, okay. So here you can write down the winning coalitions and find out the theta 1, theta 2, theta, in fact I have it, I will simply write the numbers, you can verify it later. These are the numbers. I worked it out. I hope my calculations are correct. Theta 1 is 1. Theta 2 is 3. Theta 3 is 3. Theta 4 is 5. You can check it, okay? And here the index, the Blanchard index is the vector 1 by 1 plus 3 plus 3 plus 5, 12. 1 by 12, 3 by 12, 3 by 12, 5 by 12. So that's what it turns out. You can check it. Okay, so you write down the winning coalitions and then find out which are the player 1 is a pivot, etc. He is going to be a pivot in only 1. And 2 and 3 are going to be pivot in 3 coalitions. 4 will be, because since he is having 40, is more, much more than that. Okay, so that's it. So this is used, this is useful, this index. So that is one thing I want to tell. Okay, another thing which I forgot to mention yesterday is the following. I defined the notion of the core. I'll state it as a result. You can prove it yourself. Result, let NV be a proper simple game. Then the core of the game is non-empty if and only if NV has a veto player. This result is very easy to prove. You can prove it yourself. That is for a simple game, I'm saying. In general, core need not be empty. Here also, the game may not have, core could be empty if there are no veto players. Let me recall the definition of veto. Player I is a veto. Call player I a veto player. If you remove that player from any coalition, that is losing. Like the Security Council, there are 5 players who are veto players. If any one of them opposes, nothing happens. So that's what, that is the interpretation. So the core which I defined yesterday will be non-empty if and only if the game has at least one veto. Okay, so these are the 2 things. Okay, that's it. So now let me begin my talk on matrix games. Why did I put the duster? Oh, okay. Okay. See, this is the, see, I have a matrix. There are two players, P1 and P2. P1 he has to choose one of the rows. There are m rows. He has to choose one of the rows. P2 has to choose the number of columns. Associated with these, there is a matrix A. Aij. This is m cross n. So P1's strategy is to choose rows. So he has m choices. He can choose any one of the rows. And P2 chooses columns. So 1, 2, etc. Yeah. The P1 and P2 chooses I comma j, but independently. I is an element of 1 to m. J is an element from 1 to n. If player 1 chooses I, player 2 chooses j, then player 1 gets Aij. Aij can be 0, it can be positive, it can be negative. If Aij is positive, he receives that amount from the other player, from player 2. If it is negative, he has to pay that amount to player 2. That is the interpretation. One matrix is enough. For the other one, it is simply minus of mu. This is what is called in game theoretic jargon payoff matrix. Okay. Now, the point is, player 1 wants to get the maximum amount possible. Suppose if this game is played several times, what should you do? What should he do in order to maximize his expected income? That is the problem. Player 2 wants to give him as little as possible. So they have diametrically opposite views. One of them wants to maximize, the other one wants to minimize. But instead of playing just a pure strategy, player 1 can play a mixed strategy. A mixed strategy is simply nothing but a probability vector with m coordinates. That means he chooses the jth pure choice with probability xj, the jth coordinate of x. Similarly, player 2 also can play a mixed strategy which will have n coordinates. Each coordinate is non-negative, the sum add up to 1. So let me use the notation. X is a probability vector which has m coordinates, and y is y1, y2, yn. Here each xi is non-negative, the sum add up to 1. Such a vector is called a probability vector. Same. Now if player 1 plays x, player 2 plays y, then the expected income to player 1, expected income, is given by summation, and they choose simultaneously. So you view it as independent. That is, player 1 choosing I and player 2 choosing j with probability xi into yj. So you add up to get the expected value of the joint random variable. So aij xi yj. I equal to 1 to m, j equal to 1 to m. So this is the expected income for player 1. If player 1 plays x, player 2 plays y. Now player 1 wants to, let me denote this expression as axy, corresponding to the mixed strategy x comma y played by the two players. And player 1 wants to maximize this, and player 2, in other words, what player wants to do is, suppose he knows player 2 is playing y, then he will choose that x which will give him the maximum. And player 2 wants to minimize this. So minimax. Or you can also view it this way. Suppose player 2 knows that player 1 is playing x, and he chooses that y which minimizes this. And then player 1 maximizes this. Maximum over x. See, here you are taking the maximum first, then minimum. Here minimum with respect to y. So these two, the question which Von solved is the following. This is a paper which appeared in 1928. It is when the game theory actually started from the mathematical point of view, I should say. This paper appeared in a German journal, Mathematische Analyse. This is the first paper, fundamental paper for 2%. And he proves that these two quantities are equal. So that's why it is called the minimax theorem. This is the minimax theorem, famous minimax theorem. These two quantities. See, in general, what you can show is this is greater than or equal to this. Because AXY is always greater than or equal to min of that. Now take maximum on both sides. So max x is always greater than or equal to this for every y. So minimum also. That is, this is what is called the upper value of the game, and this is what is called the lower value of the game. U is always greater than or equal to L, but what phenomenon shows is U equal to L when the matrix has finitely many rows and columns, finitely many columns. Okay, now let me start with some examples. As I told you that the proof which he gives uses fixed point arguments. Okay, very complicated arguments. Now I'm going to simply tell you the beautiful analysis of this problem from the linear programming point of view. This can be posed as a very simple LP problem, and that's what is done by George Danzig. See, you can assume without loss of generality, A is a matrix with Aij, all positive, no harm, because since Aij has mn elements, you can add a large positive integer to each one of them and make it positive. The only thing is, if the minimax of the original game is V, the minimax of the new game will be V plus n, because you are only averaging it out. So there is no loss in assuming this. Okay. The minimax problem is the following. I mean, the linear programming formulation is simply the following. Summation Aij xi I equal to 1 to m is greater than or equal to lambda. Xi is non-negative, lambda non-negative, this is for all I, and summation xi equal to 1. So I want to maximize this lambda. Maximize lambda subject to this. Okay, let me explain this. Let me give you an interpretation of how it's done. See, suppose I have two strategies, x and y, such that Aij xi is greater than or equal to lambda 1 for all j. I is equal to 1 to m. And summation Aij xi, I mean yi, I'm sorry, y, because I'm choosing, I mean, maybe if you want, I can write x1 and x2. Aij xi2 I equal to 1 to m. Suppose this is greater than or equal to lambda 2 for all j. If lambda 1 equal to lambda 2, it doesn't matter which one you choose. But suppose lambda 1 is bigger than lambda 2, I will prefer this. If lambda 1 is bigger, then I won't bother about this. In other words, that's what I am doing here. I want to maximize this lambda subject to this. This inequality is satisfied for all j. I mean, the view is simple. I mean, the idea is this one. If you have two strategies, x1 and x2 for player 1, if the one gives more income against all possible combinations of player 2, then you would prefer that. That's what. So you solve this problem. This number is what is called the value of the game. This is, I mean, this is a bounded, and lambda, of course, is not going to be more, because lambda will be at most the maximum of these numbers. It can't exceed them. So it's a bounded problem. So linear programming problem has a solution, no problem. So this lambda is precisely what is called the value of the game. This is what von Neumann defines. Value of the game is simply the max of lambda, equal to max of lambda. And it is unique. There can't be more than one. The maximum is 60.
In this case, we are maximizing A times.
Okay, but against all j. So, but see, what it means is summation aij xi is greater than or equal to this v, say, let's say lambda. Now you multiply each side by yj, lambda yj, and sum. But this is a probability vector. So this is also, in other words, axy is greater than or equal to this v, whatever be y, for all y.
Instead of maximizing the quadratic function, they are maximizing a linear function.
Yeah. That's the thing. That's why it's called linear programming. Everything is linear inequality. This idea is due to Danzig.
Maximum of the quadratic is also equal to maximum of the linear.
That's what. Yeah. And if you look at the dual of this problem, that gives, see, any strategy x naught which gives you the maximum is called optimal strategy. And such a solution exists by the linear programming methods. You know that. And if you go to the dual, but the only thing which you have to notice is normally when you write maximum, you write the inequality as less than or equal. If you recall the way you define, but that can be done without any problem. That is, what I am trying to say is max of C transpose X subject to AX less than or equal to B. That's what you write. X greater than or equal to 0. This is how you write when you write the maximum problem. But here the inequality is in the different direction. AX. But you can solve this problem because since you assume Aij is positive, this lambda has to be positive, the solution. Is that clear? See, each time you are, all the values in Aij is positive. So the expected value will be always positive. So what I do is I reformulate this problem. Let me do it. I want to reduce this to the other problem, the standard problem. Now divide by lambda. Aij xi by lambda is greater than or equal to 1 for all j. Because I know lambda is anyway greater than 0. Lambda will be at least the minimum of the Aij's. Okay, so I can do this. Now define xi equal to xi by lambda. Now what is happening? Summation xi equal to summation xi is 1 by lambda. Is that clear? Because you are going to be within the realm of probability space. Xi summation xi is always 1 because you are calculating the expected thing. Instead of maximizing lambda, you can minimize 1 by lambda. Maximizing lambda is the same as minimizing 1 by lambda. But what is 1 by lambda? It is summation xi. So this problem reduces to the following. I will write it here. Minimize summation xi subject to this one Aij xi is greater than or equal to 1 for all j, and the only restriction is xi's are non-negative. That's it. I mean, when you write down the maximum problem, this is like this. When you write the minimum, the dual of this, it will be always greater than or equal. So you reduce it to the. So what you do is you solve this minimum problem, and what you get as the minimum value will be 1 by lambda. So once you know lambda, because this value you know, so I know lambda. Once I know lambda, I know the optimal strategy. So it's after he found out, it looks a very simple problem. The matrix, I mean the minimax theorem. It's a remarkable way of converting the given game problem into a very simple linear programming problem. That's what he does. It's a wonderful achievement by Dancy, because he was trying to solve linear equations, large number of linear equations subject to large number of unknowns. So there he developed simplex method, so you can use simplex method to solve this problem. So that's what he does. So let me give you some examples. So let me rephrase what I said until now, so that you will understand precisely what I have done. So von Neumann's theorem can be formulated as a linear inequality problem. So that's what I'm saying. So this is the result due to von Neumann Dancy. You are given a matrix A of order m by n. The result says the following: there exists a unique number V called the value of the game, and x naught for the maximizer. Here I am assuming row chooser is the maximizer, and x naught for P1. This is called optimal. That does the following: Aij x naught I. I'm sorry, x naught I is greater than or equal to V for all j, and y naught for P2 such that Aij yj naught is less than or equal to V for all I. Here the summation is over j, here the summation is over I. I mean, the interpretation is very simple. There is a unique number V and a pair of strategies x naught, y naught. These are called optimal strategies, such that if player 1 uses this, his average income will be at least V, because for all j, so you are going to multiply by some probability vector on both sides. So here so Ax naught y will be always greater than or equal to V for any y which is employed by player 1, because it's a probability. And by playing y naught, player 2 is going to restrict player 1's income to utmost. So this is a saddle point actually. In the class of mixed strategies, there is a saddle point. I mean, saddle point means the following. This result can be stated in a different way like this: Ax naught y naught is less than or equal to Ax naught y, and this is greater than or equal to Ax y naught. So I have a saddle point in the class of mixed strategies, because x naught y naught are mixed strategies, x y which I write are also mixed strategies. This is what you mean by saying saddle point. But saddle point in the space of mixed strategies. So that's the thing. Okay, let me actually work out some example so that you will understand precisely what we are doing. And any x naught satisfying this is called an optimal for player 1, who is the maximizer. Any y naught which satisfies this inequality is optimal for player 2, who is the minimizer. Here, column chooser is the minimizer, row chooser is the maximizer. You can also talk about row chooser being minimizer and column. Then you write it suitable. Okay? All right. Let's look at the example which I mentioned yesterday, but probably I didn't go into it. So there are two players, there are three possible strategies. That is rock, paper, scissor. You can say 1, 2, 3 if you want, if you don't like the, but this is easier to understand. R, P, S. So this is player 1, this is player 2. So each player has 3 objects in their hand and each one has to choose one object simultaneously. There is a referee in between. So what one chooses is not known to the other player. Okay. And now I'm going to write some numbers. What are the numbers? So let me just, without wasting time, let me write the numbers. And then I'll explain what this means. 0, minus A, B, A, 0, minus C, minus B, C, 0. See, what it means is player 1 chooses rock, and if the other person also chooses rock, then player 1 gets 0. If player 1 chooses rock and player 2 chooses paper, paper can fold the rock, so player 1 loses. So it is minus A. If player 1 chooses rock, player 2 chooses scissor, rock can spoil the scissor by hitting. That's the interpretation. This game you might have played when you were a child. It's very, how to play this game? What is the best way to play this game? Of course, here A, B, C are positive numbers. A, B, C are positive. So that's why I wrote minus A. See, once, yeah, any question? Okay. Yeah. They can be different, they can be equal, doesn't matter. Okay. But they are non-zero. Okay. So here I'm going to write one possible way of doing it. Minus B, C, B, A. And then I'm going to normalize it. A plus B plus C, A plus B plus C. Because I have to play a probability vector. You can check that this is equal to 0, 0, 0. Because here minus BA plus BA, the denominator is the same for everywhere. So this is a strictly positive probability vector. Because ABC are positive, so all of them are positive. That is, you can't miss. That is, in other words, you can't say I'll play always as player 2. You cannot say I will always play rock, because the other player will know that you are playing rock, then he will start playing paper, and every time you lose A. Similarly, you cannot say you will play R and P, then also you will be punished. You have to use all these objects at some point of time with these probabilities. Suppose these probabilities turns out to be something like this. See, I'll give some numbers maybe. 3 by 6. How I got, I'm writing C is 3, B as 2, and A as 1. 1, 2, 3. I mean, I'm just giving some numbers. So this is 2 by 6, 1 by 6. This probability vector turns out to be this. If I put A is equal to 1, B is equal to 2, C is equal to 3, some arbitrary number is going to give me this probability vector. So I will use rock with probability 3 by 6. I'll use the paper with probability 2 by 6, and scissors with probability 1 by 6. But then how do you, what mechanism you will use to do this? That can be done very easily. What you do is, you take a die, toss a die. It has 6 faces. So I will say E1 is the even getting an even number. An even number. E2 is, so here I have eliminated 2, 4, 6, getting 1 or 3. E3 getting 5. So what is I mean, you assume it is a fair die. So if you toss a fair die, the chance of getting 5 is 1 by 6. The chance of getting 1 or 3 is 2 by 6. And for this, it is 3 by 6. So use this mechanism. Every time when you play the game, what you do is you toss a fair die. If it is even number, then I will choose rock. If it is 1 or 3, I will choose paper. If you get 5, I will choose this. So the other fellow cannot guess. He knows that I will be using this kind of thing. Otherwise, he will punish you. So this is how I use the mechanism. Some mechanism by which you should use. And notice, I'm going to concentrate my attention for this class of matrices. What is this matrix? Suppose I call this as A. Mathematically, it says something, because the first row is the negative of this. In other words, it is A equal to minus A transpose. Skew symmetric. The matrix is skew symmetric. Now you can ask here 0 is the value of the game. For this, 0 is the value of the game. Also, see, for the other player also the same strategy will be optimal. That is, if I use C by A plus B plus C, B by A plus B plus C, A by A, then also you can get every one of the corresponding to each column, it will be 0. That is, this strategy which I have given is optimal for both players. But this is a well-known result due to David Gale. He shows that when you have a skew symmetric matrix, the value is always 0. And if something is optimal for one player, it is also optimal for the other. Okay? It's a very beautiful result due to Gale, which he wrote it in his thesis, one part of his thesis. So let me mention that. So it is not accidental, it is just a theorem. That's what has happened. David Gale's theorem, let A equals minus A transpose. Then there exists a probability vector x naught such that Ax naught is greater than or equal to 0. That's it. And of course, you can also say there exists a vector z naught. Also, if x naught is optimal for one player, for player 1 who is the maximizer, then it is also optimal for P2. Let me tell you why. Suppose this happens, Ax naught is greater than or equal to 0. This implies x naught transpose A transpose is greater than or equal to 0. Of course, instead of column vector, it is going to be a row vector. But A transpose is minus A. This implies minus A x naught is greater than or equal to 0, or x naught A is less than or equal to 0. That is, player 1 will assure himself on the average an income of 0, and this shows that player 2 will restrict player 1's average income to 0. So 0 is the value of the game. This is true for any skew symmetric matrix. And then he uses this result to derive von Neumann's theorem. Okay, that is, given any matrix of order m by n, you can associate with that a skew symmetric matrix and use this theorem and get an optimal strategy for the skew. From that, you can recover an optimal strategy for the original game. That can be done. Okay. All right. Now, here I want to tell a result due to Kaplansky. So let me mention about that. See, I'm not giving any proof, but you can check it in the. Of course, for David Gale's theorem, you can see his book. The title of the book is Theory of Linear Economic Models. Theory of Linear Economic Models. I think year is 1960, McGraw-Hill publication. That's the company. David gave this is the book, and you can see that. All right. Now, I was talking about Kaplansky, Irving Kaplansky, a very well-known mathematician. As I used to mention earlier, he's a mathematician. He was a mathematician at University of Chicago, pure mathematician, essentially, algebra and group theory and things like that. But game theory was a hobby, I should say. He wrote 2 papers. Both are classic in my opinion. One, 1945. This appeared in Annals of Mathematics. The other one, 1995, after 50 years, this appeared in Linear Algebra and its Applications by the same author. Here, he gives a description of a class of matrices. The title of the paper is A Contribution to Minimax Theorem 1, and this is a contribution to Minimax Theorem 2. 1 and 2, that's the paper. So here, he gives a description of a matrix game in which every optimal strategy, okay, let me say what I mean by a completely mixed strategy. You take a probability vector x, x is a probability vector, x1, x2, say xm. This is a probability vector. I say that this is a completely mixed probability vector, x is completely mixed if all xi's are positive, if xi is positive for all I. That means he chooses every pure strategy with positive probability. Such a strategy is called completely mixed. Like in the example, paper, rock, scissor, the optimal strategy is completely mixed. I wrote the thing, and that is the only optimal. There is no other optimal. Okay. And now in this, he proves when every optimal strategy is completely mixed. Because you can have some strategy which may be completely mixed, some strategy which may not be, etc. But he characterizes those matrix games in which every optimal for either player is completely mixed. Such a game, he calls it a completely mixed game. So call a game, matrix game, completely mixed if every optimal is completely mixed. Every optimal means every probability vector, if he is the maximizer, it will fetch him at least the value of the game, and he uses all the pure choices with positive probability. And the same applies to the other player also. Such a game is called completely mixed. So he characterizes games which are completely mixed. So let me write out theorem because I need that. (1945). Let V, the value of the game, be 0 corresponding to the matrix game corresponding to the given matrix A. A is M cross M. Okay. That is, he is taking a game with value 0. Such games he characterizes. Then A is completely mixed. If and only if the following happens. 1, M equal to N, it should be a square matrix. 2, the rank of A is N minus 1. 3, Aij, the cofactor of the element, ijth element of this. Aij's are non-zero for all ij, and either all of them are positive or all of them are negative. That is, it cannot be one is negative, the other one, that's not possible. All the aij's are non-zero and they are all positive or all are negative. This is a complete characterization of a general game. Let me repeat what I mean by completely mixed. That means every optimal for the game is a completely mixed probability vector for both players. Okay, and this is a complete characterization, of course, with this extra condition b equal to 0. And in that paper, at the end, he makes the following remark. People didn't bother to write that, take into account. This was the comment by him at the end of this paper. Comment. Take a matrix with A is equal to minus A transpose. If n is even, such a game is never completely mixed, because if you take a skew symmetric matrix, the value is always 0. And since if n is even, use this result. The rank of that should be n minus 1. But when you go one down in the order, that becomes an odd matrix, skew symmetric. But that should be non-zero. But in a skew symmetric matrix, every odd order matrix is 0. So because of that, when n is even, such a result is not possible. He leaves this question open. What happens when n is odd? When n is odd. Of course, this result is there, but then can you simplify this result? This is for a general thing. So anyway, what happens when n is odd? That is, when can you say a skew symmetric matrix of odd order is completely mixed? Of course, you can use this, but can you do it in a different framework? It does it. And also it's very beautiful, and especially for people who have the mathematics background, you will appreciate it better. He comes up with a brilliant idea. See, in order to describe what he has done, I have to say a few words about this term, Pfaffians. What does it mean? What is a Pfaffian? Let A equals minus A transpose. I am assuming, because I am in this, so I can use it, no problem. See, let's see if n is odd, Pfaffian of A is 0, defined to be 0, because the matrix is 0, the determinant is 0 corresponding. So if n is even, we have to define. N is even, how do you define this? No, sorry, I'm sorry. Okay, that's okay. If n is odd or even, how do you define? Okay. Maybe I am using the notation in an abusive way, but it's okay. All right. I'm going to assume that n is odd to define the notion of Pfaffian. N is of the type 2m plus 1 odd, and A is equal to minus A transpose. I'm going to define the P1 Pi is simply the ith principal Pfaffian corresponding to the skew symmetric matrix. That's what I'm going to define. Of course, the entire matrix Pfaffian is 0 because it is odd. I already told you. But I'm going to define a specific thing, ith principal Pfaffian. That means You leave out the ith row and the ith column. Now you have a square matrix of even order, which is also skew symmetric. Okay, and we know that the determinant of an even matrix is nothing but the square of a polynomial. The entries of the polynomial comes from the elements of that thing. Let me give a, this means Pfaffian of omit ith row and ith column. Let me denote this matrix as Bi. Bi is a submatrix of A, ith row and ith column is omitted. It's a submatrix. It is of even order. I can talk about the Pfaffian of an even order matrix. So let me give you the precise definition of Pfaffian. Why did I keep the, okay. If it is a 2 by 2 matrix, suppose A is, maybe I use some different notation. If M is say 0, A minus A, 0. What is the determinant of this? Determinant of this is A square. So Pfaffian of M is simply the number A. If it is negative, Pfaffian is negative. If A is positive, Pfaffian is. In other words, this is nothing but square root of determinant, but the sign will depend on the sign of A. Because the square root could be either plus or minus A. You understand? So here, if A is positive, Pfaffian will be positive. If A is negative, Pfaffian is negative. The sign. Now let me go to the fourth order, 4 by 4. 0, A, B, C, 0, D, E, 0, F, 0. The other thing you can complete because it's a skew symmetric matrix. So it is these ABCs are, some of them may be positive, some of them may be negative. So I'm not assuming anything. These are real numbers, that's it. All right. What is Pfaffian? Pfaffian of this 4 by 4 matrix. Here M is 4 by 4. Pfaffian of M is AF minus BE plus CD. AF minus BE plus CD. And the determinant of this is simply AF minus BE plus CD the whole square. This is the polynomial, B. Okay. So it is the square, this is nothing but the square root. The positive or negative will be determined by the sign of this. If this is positive, Pfaffian will be positive. If this is negative, this will be negative. Pfaffian will be negative. So the sign, the square root, whether you have to take the positive square root or the negative square root, depends on the sign of this. So you simply define some. But how do you do it in general? Okay, so I've done this, but let me give you the general definition. M is of even order. M is 2n cross 2n. N could be 1, n could be 2, etc. is even. Okay. So what I do is, now I have 2n integers. So 1, 2, etc. 2n integers. So this is the set. Now what I'm going to do is, I'm going to take I1, I2, In. This set is a subset of this. This I1, I2, In, I am choosing n integers out of that, calling it as I1 could be 2, I2 could be 4, etc. But I am picking out n integers from 1 to n. Okay. Now what I do is I form corresponding to I1 I write J1, corresponding to I2 I write J2, corresponding to IN I Jn. So this the union of this will cover the entire set. Is it okay?
The permutation.
Yeah. That's what I'm going to. Yeah. See, this I1, I2, IN is some subset, but J1, J2, Jn is the remaining integers. I am attaching J1 to I1, I2, J2, etc. The only condition I demand is Ik should be less than Jk. Ik should be less than Jk for k is equal to 1 to n. Okay. All right. Now this 1 to n now go to I1 J1, I2 J2, etc. Ik Jk. This is the permutation. That is the first integer go to I1, the second one go to J1, the third one go to I2, the fourth one go to I2. Then you get the permutation. I and J, that's right. Okay. So this will give you the sign also for the permutation, whether it is positive or negative. Now what I do is I from this element I calculate this m I1 J1, m I2 J2, etc. m I n Jn. That is I1 J1 is an element, that is I1 throw J1 column, I2 throw J2 column, etc. And then I am multiplying. The sign of this is given by the permutation of this. Okay, sign, I will simply write sign. Whether it is going to be plus or minus depends on the permutation. Okay. Now this I do for all such possible I1, I2. So now I summation over this over all possible I1, etc. IN satisfying these conditions. I will do it with reference to 4, n is equal to 2. Is that clear? Now this is what is called Sophian of the matrix M, the entire sum. This is the so you have a even order matrix. I pick n integers from this, and then I'm attaching J1, J2, Jn. With I1, I'm attaching J1, I2, J2, In, Jn, with the only condition that Ik should be less than Jk for all k equal to 1 to n. Now what I do is I multiply these elements m I1 J1, m I2 J2, etc. m I n Jn. Now the sign of this is determined by the sign of this permutation. Okay. And then add over all such possible things.
What is the difference between determinant and definite?
Huh?
What is the difference between determinant and this?
No, the square of this is the determinant. That's what it is. Because that is a very well-known result. That is, when you have a skew symmetric, because it is skew symmetric, remember, m is equal to minus m transpose. I am defining it only for this. Very important. Okay. The determinant of a skew symmetric matrix is always a polynomial square. That polynomial is this. The elements come from that. The square of this gives you the determinant. It's a well-known result in skew symmetric matrix. It is easy to prove. I mean, it's not difficult to prove. Yeah, that is the connection. That is the square of that gives you the determinant. So whether you have to take the positive or negative depends on all these aspects. Because the square root could be either positive or negative, isn't it? Okay. Now let me do this for 4. N is equal to 4. I mean, n is equal to 2, sorry. For n is equal to 2, I will do it. See, what is this? So I have 1, 2, 3, 4, 2n. Okay. Now I pick 1, 2 as my subset. See, with 1, I cannot attach 4. No, I can. So with 1, I attach 3, 4. This is one way of doing it. This is one possibility. With 1, 2, I can attach 3, 4. Because 1 is less than this, 2 is less than that. This entire thing covers this. With 1, I can attach 4. And with 2, I can attach 3. There are two ways of attaching with 1, 2. One is 3, 4. The other one is 4, 3. Okay.
Usually to take 2, 4. Usually to take 2, 4. 2, 4 if you take.
2, 4. You mean this one? This is not possible. The first one should always be 1. The I1 should be always 1. Because, you know, see, suppose you leave out 1, why do you put it? Because I already told you, Ik should be less than Jk. If you choose I1 as 2, 1 should go with 2 or the other one. All of them are bigger than 1. So always I1 is 1.
No I2, J4.
That's right. You are right. The last also is not possible. That's right. These are the two things which you should observe immediately. Your question is well intended. Good. You asked that question. I1 can never be 2. It should be always 1. Okay? Yeah. So if you form this way and you write out the thing, you will see what I wrote will be the, that's how I wrote it. This is how it is done. Okay. Now let me relate this to Kaplansky's paper 1995. He relates this to completely mixed game of skew symmetric matrices. It's a very beautiful result. Okay, let me say that. Okay. Because I wrote 1, 2, the other one should be 1, 3, I should write 1, 3, 2, 4. So there are 3. I have omitted 1, 3. Because I write 1, 2, I can also have 1, 3. For 1, 3, it is 2, 4. So there are 3 terms. That's why I wrote 3 terms in the Pfaffian corresponding to the 4 by 4 matrix. Okay. All right. What is the result of Kaplansky? This is the result. Theorem. Let A equal to minus A transpose 2m plus 1 cross 2m plus 1. It's an odd order matrix. Because if n is even, we know that it can never be completely mixed. It should be of odd order. Be completely. Okay. Then A is completely mixed if and only if okay. I have to define this term, but I'll do that. P1, P2, etc. P2m plus 1. These are called principal Pfaffians. If this vector all are, I mean, if P1, P2 are all different from 0, and alternate in sign, and alternate in sign. That is, if P1 is positive, P2 should be negative. If P1, I mean, this will be of this type, plus, minus, etc. plus, or it should be minus, plus, minus. Only 2 possible. All are different from 0. and also they should alternate inside. So this is the result of, yeah. Is it okay? Oh, okay. Huh? Oh, okay.
This was proved after 50 years of.
Yes, yeah. Because see, it is in honor of somebody's 60th birthday or something. So it was published in linear algebra. It's a beautiful result, I should say. Maybe I'll continue later. Yeah, in 1 minute, let me say this. See, this is a result. I asked one of the students from CMI to look at it, whether you can do it from a different angle, the same thing, instead of Pfaffian. Pfaffian is something which is, from the game theoretic point of view, can you do it? He has done it, connecting it with LCP. I will talk about it when we meet after this. Okay, that's the. So that result probably for people who do not know the definition. Okay, here I have to define the principal Pfaffian. I have not done. What is PI? PI, omit the ith row and ith column. What you are getting up is an even number. I can define the way I have done that. Okay, that's what it is. I means it can go from 1 to 2m plus 1. So P1 is a principal Pfaffian, P2, etc. P2 means omit second row, second column. You get an even number. You define. So what it says is all those principal Pfaffians should be different from 0 and they should alternate in sign. And not only that, for this, he proves one significant lemma. That lemma is crucial for the proof. That is, he proves the following lemma. It's a crucial lemma. Let B be the matrix obtained from M Bij if you want. That is omitting the ith row and the jth column. Okay, I'm not writing. Omitting the ith row and jth column. Then determinant Bij, and A equals minus A transpose. Order is 2m plus 1 cross 2m plus 1. All these are there. Now I'm looking at it. Then Bij, the determinant of this is nothing but Pi Pj. Of course, you can do it by looking at, because the diagonal things, you look at it and the sign, you can prove it. One of my students did that, but he proves it in a different way. He proves it by so. But odd is important. This lemma is not valid if the given matrix is even. Okay. So this is a crucial thing, and the rest, and he uses his first paper result to prove this. Okay, I'll stop it.